features in different configurations, their advantages and limitations. Okay, so let's start. Before that, I'd like to have a small, we have a we got prelude of this talk, of this lecture. How
Sir,
yes,
sir, will there be a box available because I couldn't find any, sir?
box should be there. I'll check it later. Okay.
All right,
So,
sir. Thank you so much, sir.
So it would be helpful if you give the links. I also couldn't find it.
Yes,
okay,
sir.
Yes, sir.
I'll try to find it out what happened to box, if
Sir,
it is
okay.
activated or not yet. So try to look into it. Okay, so before we start, I'll give a brief introduction how it all started, the analog integrated circuit, the little bit of historical background. Okay, in device 2, we discussed about the feedback amplifiers, if you remember. At the beginning of the 19th century, Harold Black, an electronics engineer from Bell Lab, he was looking for an amplifier that would give a stable operation, a stable gain, because they needed to boost the gain of the telephone lines, right, that were stretched over hundreds of miles. So they needed to boost the gain every few miles because the gain would drop. Now, the gain of the amplifier, as you know, is dependent on many different factors, and most of them, one of the major factors that affects most is the temperature. So he was looking for an amplifier that would provide stable gain, or looking for a technique to stabilize the gain of the amplifier. So in his quest to find an amplifier with a stable gain, he developed this technique of feedback, right? And that's how all it started, the feedback technique, and that has become ubiquitous in almost all, engineering and science, right? So feedback amplifier, let's take a look at it, what are the different components and how it looks. So we have the different components of feedback amplifier. Okay, pause.
Sir, are you writing? Nothing is showing, sir.
Hello guys, can you see the screen?
Yes,
Yes,
sir.
sir.
Yes, sir. Now you can see.
So can you recognize this diagram here?
Yes, a closed loop feedback.
Yes, sir. Close the feedback system.
Right. So this was something we discussed in device 2, or it has been discussed, right? Has it been discussed in your device 2? I mean,
Yes, sir.
okay.
Yes, sir. Positive and negative feedbacks were discussed.
Right. So this one is negative feedback. Why it is negative?
So because the XF part, the negative, there is a negative.
Sir,
Right, so
because
this is
yeah, sir,
negative.
so because the
Feedback.
error is counted here, so we need negative feedback.
Because feedback signal is deducted, right, from the source signal. So, and our input signal to the amplifier, is Xi, the input signal, is the difference between our source signal and the feedback signal, right? So that's why it's called negative, right? Negative feedback. And here is the gain, A is the gain of the basic amplifier, which is the output divided by the input signal, which is Xi. And beta is our feedback factor, which is the output of the feedback network XF divided by input is output signal X0. So that's known as the feedback factor, right? And our overall gain, which is also known as the gain with feedback, AF, which is the ratio of the output signal divided by the source signal XS. So that is our output divided by the input XS. So that is our overall gain, or gain with feedback, because that includes also the feedback network. And that, what is the expression for this overall gain? Do you remember?
AF,
Yeah, AF is here, and AF equals what?
sir, gain with feedback.
Yeah, this, what is the expression for this?
Sir, X.
Sir, X not divided by
not
XS.
divided by XX.
And that's equal to what?
Sir, A by 1 plus A beta.
Right, that is A divided by 1 plus A. Right. So in this case, and from this expression, if you see that if our this product A beta is much larger than 1, right? And then we see that be reduced to 1 over beta. Right? This A will cancel out and reduce to 1 over beta. So beta is completely determined by this feedback network, and which is
Sorry, screen freeze হয়ে আছে.
why is we are having this problem?
Sir, actually only share a particular screen, sir. এটা স্যার এই প্রবলেমটা হয় স্যার.
হ্যাঁ
হ্যাঁ স্যার, আপনি যদি স্পেসিফিক ভাবে একটা স্ক্রিন শেয়ার করেন তখন এই প্রবলেমটা হয়.
আমি তো একটা স্ক্রিনে আছি।
আপনি পুরো পিসিটা শেয়ার করেন, মানে এন্টায়ার পিসি
স্যার
স্ক্রিন,
ইন্টার
তাহলে
স্ক্রিন করলে আবার এই সমস্যাটা হবে না.
তখন আর হবে না স্যার।
জি স্যার.
তো আপনি মুভ করলে চেঞ্জ মানে দেখা যায়।
But we didn't have this problem before. So different times, different problems. Is it visible on the screen?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so what we have got here, that our gain with feedback AF is 1 over beta, right? So that means that is independent of the gain of the amplifier A, right? So the overall gain or gain of the feedback amplifier does not depend on the gain of the basic amplifier. It is determined only by the feedback factor, beta. And as we know that gain of the amplifier, it can vary based on different factors. Temperature is one of the factors, and there are other factors, just manufacturing these limitations, right, to get the exact values for the different parameters. And so it varies from one transistor to another transistor, one amplifier to another amplifier. So these are factors that affect the gain of the basic amplifier. But feedback factor is mostly made of resistive element, resistors, and resistors are their value do not change that much, right? Very little change with temperature, and that is negligible. That doesn't affect the overall output. So we can have quite stable gain of the amplifier, stable and predictable gain for the amplifier. So, but for that, the condition that needs to be satisfied is that a beta should be much larger than 1, right? So to have large gain, you need beta to be small, right? Otherwise, AF will be, if beta is high, so AF will be low. So to get high gain, you maintain low beta, right? So in order to satisfy this condition, you need to satisfy this condition. A beta has to be much larger than 1. That means the gain A should be much larger than 1. Or we can say should be much larger than 1 over beta. So we need a basic amplifier that condition that it needs to satisfy should have a very high gain. The higher is the gain, the more precise will be the overall gain of the amplifier. So ideal condition, if your gain is infinite, right? If your gain is infinite, then you see that AF will be, you can write, this is what we have, the actual expression, and this you divide by A, you end up with this expression plus beta. In case ideal situation A is infinite, so this reduces to 1 over beta. So that is our ideal condition, ideal gain, right? Ideal in ideal condition. And that's why we say that ideally op-amp should have infinite gain. Then we can write that AF is 1 over beta. It's the ideal condition. So, but practically we cannot have infinite gain, but we try to make it as high as possible. And op-amp gain, as you know, it has very high gain, about 10 to the 5 to 10 to the 6, right? So that is quite high, right? So that is the main, reason why the op-amp comes with such high gain. In order to satisfy this condition, right, that A beta is much larger than 1, and so that the overall gain is completely independent of the gain of the amplifier, is determined only by the feedback network, this beta. And in our what is that? In our op-amp, what is the feedback network? That is the R1 and R2, right? The two resistors, right? We have, if you remember in op-amp, what we have. We take from the output, right? We connect a resistor here, and then we connect another resistor, right? And then this one we connect it back, right? And then we call it R1, R2, right? Something like this, right? We have, you remember the op-amp. If we show it like this, there we have negative, positive, there we show negative. Then we can show it like this, R2 and R1. Right? So this is your input signal, and this is your output. And so that is our feedback network, right? And this R2 and R1 is for feedback network. And that is our feedback voltage, VF is XF, right? So that is going here. And here the feedback factor beta will be your VF by V naught. And that's the apply the voltage division rule. And that will be R1 divided by R1 plus R2. And you take the inverse of this, 1 over beta. So 1 over beta will be R1 divided plus R2 divided by R1. And that will be 1 plus R2 by R1, right? So we know that is the gain of the op-amp non-inverting amplifier configuration, 1 plus R2 by R1. So, and that is what we apply the feedback theory, and gain is 1 over beta. And beta is this, that's the feedback factor. So you see, feedback factor is determined only by the resistance values. It doesn't depend on the amplifier gain or the op-amp open loop gain. It doesn't depend. We ignore this one because it's very high. And that's also the ratio, right? We take the ratio. So any change in the resistance values will be cancelled out because you're taking the ratio, right? So we get a very precise, stable, and predictable gain, right? Is that clear, guys? Any question?
Yes, sir.
Okay. So this all started with this development of this theory of this feedback amplifier or feedback technique, right? So we need an amplifier, basic amplifier with a very high gain. Now there are other requirements, right, that needs to be satisfied. There are one requirement that at the input side, we need to take the difference. We need to take the difference between the source signal and our feedback signal, and that has to be precise, right? The circuit or whatever device that we should use here should be very precise in taking this difference, right? Otherwise, if this is not precise, if it is not accurate, then the output will not be accurate, right? Output will not be accurate. So we need a precise mechanism, right? So to take the difference signal here, right? So at the input side, what we need to develop some mechanism, right? So that is able to take the difference between these two signals, right? One is our source signal, the other is the feedback signal. Right? So first we take the difference, right? And then we need to amplify, and this should have a very high gain, right? So we need an amplifier, right, with a very high gain, right? So first you take the difference, and then you amplify that signal, right? And then at the output, you connect the load, right? You connect the load at the output. But amplifiers are designed to handle, low power, right? Not large power or large current, but load will demand large power, large current. Different load will demand different amount of power, different amount of current, right? So usually it depends on the load, right? But we don't know. So in order to provide large current to the load, so what we do, we add another stage at the output. So we have an output stage. Output stage. So usually we have the amplifier here, right? So that will enhance the gain, and then output stage that will enhance the power. So usually it is a power amplifier at the output stage, or also known as the voltage buffer. Voltage buffer because it will have a gain of 1, right? The voltage gain, it will not increase the gain, but it will increase the amount of power, right, that is needed by the load, right? So usually when we say large power, it implies large current, right? So the amount of current will be increased, right? So we need another circuit here, usually a voltage buffer, power amplifier, that will enhance the power level, right, the signal. So that is how it will look like. So this whole thing, at the input side, we need a mechanism to take the difference between the two signals, that should be amplified, and then that amplify, mostly when you say amplifier, so mostly it amplifies the voltage level, not the current level. Because if you want to increase the current level, that becomes induces a lot of noise, right? And a lot of heat dissipation. So usually current level is kept low unless it is absolutely necessary, right? So usually this amplification of the voltage is done in the amplifier stage, and then at the output stage, the current level is increased, that can satisfy the current requirement of the load. So thus we get the 3 stages, right, for this to implement this feedback system, right? And now here at the output, you connect your feedback loop, right? And that feedback will go into this XF, right? So that you have the feedback network. Right? In the case of op-amp, we have just 2 resistors here, R2 and R1. So we can also show it like this. We have R2 and R1, 2 resistors, and that just goes to this input side. So at the input side, this system here that takes the difference, usually we also call it difference amplifier. Difference amplifier. So this difference amplifier, then we have the basic voltage amplifier, and then we have our output stage, the power amplifier or voltage buffer. So all these three components together. So these three components together make our what is known as the op-amp, right? So these three together is our op-amp, right? So op-amp was basically developed, right, to meet the requirement, right, that is needed to implement this feedback amplifier, right? So then you can then just add the two these resistors externally, and you get your amplifier, which will give you a very precise and stable gain. Any question, guys?
So what's the RL is used for?
Sorry?
The resistor RL. Why do we need it?
RL is the load, no? You don't need it, but
Oh,
you
okay.
have to,
Yeah. Okay, sir. I didn't get this.
all
It was
because of the
load.
load, right?
Yeah. Okay, sir.
Sir,
Yes.
sir, what is in the at the left of the amplifier op-amp? Is it a gate or something, sir?
And the
AMPL.
input side, right?
Yes, sir. AMPL input side.
Input side that we call that, so we need to take the difference of the two signals, right?
Yes, sir.
So this is taking the difference between these two signals.
No, sir, not this one, sir. What
Which
is the gate look like, sir? Between the drift amplifier and amplifier, there is a small gate look like
This one?
Yes, sir. Yes, sir. Yes, sir.
Oh, this one just an arrow sign.
Oh, okay, sir.
Showing
Okay.
the signal flow direction. Arrow sign is no good. And
Sir,
flow of signal. Yes.
Sir, in 207 we studied that we use op-amp as a voltage buffer. So here you are saying this whole thing
Sorry?
is a... Sir, in 207 we learned how to use the op-amp as a voltage buffer. And here you are saying this total thing is a op-amp. Sir, I didn't get this actually.
Yeah, op-amp as a voltage buffer. Right, whole op-amp as a voltage buffer. Right, but inside the op-amp you have another buffer.
Oh,
Right.
sir. Oh, now I get it.
Okay. Inside the op-amp itself you have another buffer, but op-amp we are using as an amplifier, but we can also use as a buffer if we want to transfer a voltage signal from one circuit to another circuit. Right? So then you design the op-amp or connect the op-amp so that it works as just a voltage buffer with gain 1. Right? Is that clear?
Yes, sir.
Okay, and another reason to add this amplifier, if you don't need to enhance the current, actually what happens, the current level here in the basic amplifier, usually in the microampere range, right? Current level is kept lower, usually in the microampere, nearer to microampere, right? And in the buffer, right, it will be raised to at least milliampere range, right? If not too high, but at least in milliampere range, so that you can at least perform some regular, operation. But there are high power op-amp as well that probably you can further hundreds of milliampere or maybe ampere. If you want ampere range current, then you add another power transistor at the output, external to the op-amp. But usually op-amp that mostly they are designed to handle at least current in the milliampere range. The op-amp that we use in the lab that can handle current about 20 milliampere maximum. Right? But the amplifier in the op-amp that amplifies the voltage, the current is kept in the microampere range. Right? So otherwise the power consumption will go too high, and that will increase the temperature, and lot of heat will be dissipated, and that will deteriorate the performance of the chip, right, and reduce its lifetime. So there are many issues with the high current. So that's why in the amplifier, the current level is always kept low, mostly in the microampere range. Is that clear, guys?
Yes.
So that was the main, beginning, the main motivation behind the development of the op-amp. Op-amp was developed in 1970s. That's almost 50 years back. So first they developed this difference amplifier. Right, we'll see how the circuit we can construct this circuit and design this difference amplifier circuit, right? And then we have this amplifier, multi-stage amplifier probably, or amplifier with some active load to have very high gain. And then we add the voltage buffer, all these circuits integrated on one single chip, right? We call it op-amp. So that is the beginning of our analog integrated circuit, and that probably most popular and useful analog IC chip. So now we start our review of the single stage transistor amplifier. So transistor, as you know, it has the 3 terminals. So there are 3 amplifier configurations, right? Do you know what are those 3 configurations for the transistor?
Sir, common emitter, common collector, common
Common base, sir.
base, sir.
Right. Common emitter, common collector, common base. Right. So what are the differences between these 3 configurations? There are structural difference, right? And there are difference in their characteristics, right? Properties, right? Features. Now, structure-wise, when we say the common emitter means emitter will go to ground, okay? Emitter will go to ground, and then we apply signal at the base. Our source signal goes into the base. Is our source resistance. And we take the output from the collector. So we connect our load to the collector, or load resistance. It's our output, right? And this is what we call common emitter amplifier. So here emitter is common, see? Emitter is common to both the input and output. Input we apply between base and emitter, output take from collector and emitter. So that's why the name common emitter. So then common collector, when you say common collector, what we do? In common collector, we'll ground the collector. Common collector will be grounded. And we apply the input at the base again and take the output from emitter. The output is taken from the emitter. So this is our common collector amplifier. And when you say common base, for common base, what we have to do?
স্যার একটু যদি স্লো যাইতেন নোট করতেছি তো স্যার একটু টাইম দিলে উঠাইতে পারি
Sir, base will be grounded, sir.
Base will be grounded, right? So common base will be grounded. And what do we apply the input?
Sir, emitter.
Right. Input we apply to the emitter. Input applied to the emitter and output
From collectors.
and output take from collector. Oh, it's common base, sorry. So there's common base, and common base is grounded. As you can see here, base is common, right? Base is common to both the input and the output. Right? The input we apply between emitter and the ground, that is base, and output we take from collector and the ground, which is collector and base. Right? So base is common to both the input and the output. So it's the name common base amplifier. Any question, guys?
Yes, sir. Sir, আমরা স্যার কালেক্টরে ইনপুট আর এমিটারে আউটপুটটা দেই না কেন স্যার? রিভার্সটা?
এমিটার থেকে আউটপুট নিচ্ছি আমরা
স্যার আমি স্যার কমন বেজের এই কনফিগারেশনে আমি মানে কালেক্টরে ইনপুট আর এমিটারে আউটপুট নেই না কেন? মানে
কালেক্টর থেকে কখনো আউটপুট নেওয়া হয় না, বিকজ কালেক্টর ইজ না, ইনপুট অ্যাপ্লাই করা হয় না, কারণ কালেক্টর ইজ রিভার্স বায়াসড।
ও ওকে স্যার,
ঠিক আছে। ইনপুট ইজ অলওয়েজ বিটুইন বেস এন্ড এমিটার।
ওকে স্যার।
Now these circuits we call conceptual circuit diagram. Why do you call them conceptual? These are not the actual, common emitter, common base amplifier circuits, right? Because they are missing something.
Yes, sir.
What they are missing?
The capacitor.
Capacitors.
Yes, sir.
Anything else? Anything else they are missing?
Sir, external voltage VCC.
Right. Actually, the biasing circuit. Right? The biasing circuit. What is the biasing circuit? These are actually without biasing circuit, right? These circuits are without biasing circuit. What do you mean by biasing circuit?
Sir, portion of device circuit which supplies steady voltage or current, sir?
The DC voltage, right?
Yes, sir. DC
DC
voltage.
voltage and current to the transistor. Circuits that are used to power up the transistor. So you need to bias. Biasing is like powering up the transistor. Otherwise, transistor as it is will not work, right? Why it will not work?
Sir, because the base emitter will be reverse biased
Because of?
without biasing.
Because transistor is PN junction, right? Combination of, there are two
So
PN junctions.
yeah,
And
the
they
sir,
need to be, yes.
so it's because of the internal voltage, so like 0.7. There is a barrier voltage inside the
Right.
transistor. We need to cross that voltage.
Yeah.
So biasing is needed.
Right. So you need to forward bias or the reverse bias the PN junctions, right? With DC voltage, right? So unless you forward bias, reverse bias the junctions with the external power supply, right? The transistor as it is cannot work, right? They will not respond, right? So these circuits I have shown to just, show you the main concept, right, of the different amplifier configurations, right, that distinguishes the different configurations, the common emitter, common base, common collector, right? What are the distinguishing features? Features here not characteristic features, but structural, right? Structural features. So common base will be grounded, common emitter will be grounded, common collector should be grounded, right? And how we apply the input and take the output from this transistor, and to show those different aspects. Now, in order for these transistors, the amplifiers to work, right, you have to bias, right? And we want to use this transistor as an amplifier. We can use the transistor as an amplifier, right? That's what our objective is, right? To use the transistor as an amplifier, or we can also use this transistor as a switch, right? Now, the biasing mode will be different, right? If you want to use this as an amplifier, or if you want to use it as a switch. So what will be the mode of biasing if you want to use this as an amplifier? Hello guys.
No idea, sir.
Yes, sir.
What will be the mode of biasing for amplifier?
It's a forward biased.
Yeah, we forward bias the PN junction, right? Forward
Yes, sir.
bias, reverse bias. So, but mode the of biasing for the transistor, right? There are three modes. Do you remember?
Yes, sir.
What are those three modes?
So it's common emitter.
No, that's configuration. No, it is-
So active mode, saturation mode, sir.
Right, active, saturation, and
Cut off.
cut off. Right. So three modes: active, saturation, and cut off. So if you want to use this transistor as an amplifier, we have to bias it in active mode. And if you want to use this as a switch, then what are the modes
So
for switch?
cut off and saturation, sir.
Right, it has to be saturation, and the other is cut off. So saturation mode, the transistor will be on, the switch will be closed, and cut off, the transistor will be off, switch is kind of open, right? On off. So we need to bias the transistor in active mode because we want to use this as an amplifier. So to bias in active mode, what are the conditions? How we can bias it in active mode?
ফরওয়ার্ড বায়াস হবে
Hmm?
স্যার এমিটার স্যার ফরওয়ার্ড বায়াসড হবে
Emitter? Should be emitter.
Sir, base emitter forward bias and sir, base collector reverse bias.
Right. So we have
স্যার
two
সব
PN junctions. One is the base emitter, right? So that has to be forward biased, base emitter junction. The other is the collector base junction that has to be reverse biased. So reverse bias means positive here, negative here, right? So this is an NPN transistor. NPN transistor. So we need to forward bias this junction, the plus on this side, minus on this side. And collector base junction reverse bias, plus on this side, minus. So active mode means the emitter base junction forward biased, and we have the other collector base junction has to be reverse biased. So that we have to ensure, right? And what are the situation in saturation and cutoff these modes?
Sir, both forward bias and both reverse bias, sir.
Right, in saturation both junctions are forward biased, and cutoff both junctions are reverse biased. Okay, so now we know that we need to forward bias the emitter base junction and reverse bias the collector base junction. Now how do we do that? So there are different ways to bias the transistor amplifier, but this is the one that is most popular. So this is the biasing circuit. So that shows the VCC, the supply voltage is applied to this transistor through the network resistors R1, R2, RC. So through RC we get a positive voltage here. Right? So that will reverse bias this junction. And then through this network of this R1 and R2, a voltage will appear here, the VB, right? So that will forward bias this base emitter junction. So this is how we can achieve this. And one thing we need to ensure here that so this is our VB here. Sorry, VC is the voltage. In order for the junction to be reverse biased, VC has to be greater than VB, right? So that means this collector base junction will remain reverse biased. VC has to be greater than VB. And for this junction to be forward biased, VB has to be greater than VE, right? So for emitter base junction to be forward biased. So that is our voltage VBE, right? Usually for silicon PN junction, VBE is about 0.7 volt, right? So we have to ensure that voltage here, VB, the base voltage, has to be greater than VE, right, by 0.7 volts. So that means VB will be VB plus a current will be flowing here, the emitter current, which you can denote by IE. So that will be IERE, right? So the voltage, this total voltage has to be greater than 0.7 volt, right? Because VBE has to be 0.7 plus this voltage. So we have to ensure that VB, this voltage is greater than 0.7, right? So this junction is forward biased. And another thing that this total voltage, VB has to be, VB is less than VC. VB is less than VC, right? So that junction is reverse bias. And what is VC? VC is if a current IC is flowing here. So VC will be your VCC minus ICRC. VC will be this. So this voltage has to be less than this voltage. So designing the biasing circuit, right? So this is also a critical part of designing the amplifier, right? So this is for, this has to be forward bias and this has to be reverse bias. This you have to ensure, but this is not all, right? Biasing means this has to be forward bias, has to be reverse biased to be in active mode in the first place, but that is not all. There are more to it. There are more to it. And what is that? Because you need to, it has to be connected to a load, right? When you operate the amplifier, this will be connected to a load, right? And load will draw a certain amount of current, right? IM, right? And this IL, the load current, it has to be supplied by this transistor. So this IL basically will come from IC actually, right? So you have to ensure, because load current is it will be an AC current, right? Signal current is an AC, right? Let's say this is our IL, right? So it will have a maximum value, right? IL max, right? So then you have to ensure that IC, the DC collector current, should be larger or at least equal to the maximum value of the load current, right? Otherwise, you have biased the transistor in the active mode, that is okay, but your transistor will not be able to supply the required current to the load. And when the load current will try to exceed IC, it will turn off, transistor will turn off, right? So that is one requirement you need to satisfy. So in designing amplifier, you need to know how much current is needed by your load and design the amplifier accordingly so that your amplifier can supply that much current. And to ensure that, you have to ensure that the collector current is greater than or at least equal to the maximum value of your load current. Is that clear, guys? Any question?
No, sir.
Okay.
Okay, so designing the biasing circuit, that is one requirement you have to ensure. What is the other requirement about voltage? Now, there will be output voltage, load current, and there will be output voltage or load voltage, whatever. This is also signal voltage, right? Now, here you have the voltage VC, right? Now, this voltage is AC voltage, right? And voltage here is DC voltage, right? So basically in the amplifier circuit, you have both AC and DC voltage, right? Because DC is needed to power up the transistor, and AC is the actual signal current or voltage that you are trying to amplify, right? So at any point of the transistor at any time, you have two types of signal. One is DC and one is AC. So the like DC collector current, we can write it I, small I, capital C, is summation of DC current, capital I, capital C, plus AC current, small I, small c, right? So that is our total collector current, right?
স্যার ইকুয়েশনটা বুঝলাম না স্যার। আইসি ইকুয়ালস টু বড় আইসি প্লাস আবার স্যার একই জিনিস লিখছেন স্যার, ছোট আইসি।
Yeah, this is I with the capital C.
Oh, okay, sir.
This is I with the small c, right?
Okay,
so
sir.
DC collector current plus AC collector current. Together, this is the total collector current. Similarly, the collector voltage, we have small v with capital C. And this capital C. Let's try to make it bold. Small I with capital C, small v capital, total collector voltage will be summation of DC voltage, small v, capital V, capital C, plus small v and small c. So that is our total collector voltage. So at any point of the transistor circuit, amplifier circuit, you will have the both, right? Whether VB, you will also have not only DC, also you'll have AC, which is small v, small v. Also at emitter, you can have both, right? Capital and the DC and AC, right? So you have both. Now, how it will vary? Now, if I draw the diagram here. So this is time, and this is our voltage, right? Now we have, let's say this is our total voltage, collector voltage. So there's a total collector voltage supply, VCC, our total collector voltage, total voltage here, supply voltage. Then VC will be lower than VCC by the drop in ICRC, somewhere, let's say here, our DC collector voltage VC. And the difference here, this difference will be ICRC, right? The drop that we have here, right, ICRC. And less that is we have VC. Right? Then VB will be lower than VC by this voltage VCB. Let's say this is our VCB. So this is somewhere, let's say we have VB somewhere here. Right? So let's say we have VB somewhere here. Right? So this difference here, right, is our VCB. The collector to base voltage. So these are the DC voltages. Let's say our DC voltages are like this for this transistor amplifier. So now we have signal voltage VC. So how it will fit in here, right? So VC, this collector voltage, the AC collector voltage, will be superimposed on this DC collector voltage. See, these two will be superimposed on each other. So if you superimpose this AC voltage on the DC collector voltage, so the total voltage will look like this. Let's change the color. So the total collector voltage, when AC collector voltage superimposed on the DC, it will look like this. So that will be our, total collector voltage, small v with capital C. These are our total collector voltage, how it is varying, right? And this will be our, this difference, our maximum value of the output voltage. So this is our maximum value, peak value of the output voltage. So one thing is obvious from this diagram, that your Vomax, the maximum value of your load voltage, should be within this limit, right? This should be less than or equal to VCC minus VC, right? This difference, which is ICRC. And also it should be less than VCB, right? It should be also less than or equal to VCB, right? Vomax, right? Or in other words, if your load voltage demand, the load voltage demand, you know how much voltage is needed for your load, right? Then this difference, which is also your ICRC, right? So this has to be greater than your Vomax, or at least equal to, and VCB also has to be equal to or greater than Vomax. So that means this voltage drop that you need here, or the voltage drop that you need here, should be enough, large enough, right, to support the maximum value of your output voltage, right? So VC you have to, set accordingly, right? You have to set the VC value, the collector voltage, DC collector voltage, appropriately, right? So that it is somewhere in between, so that it can, accommodate this AC collector voltage, both the positive half and the negative, in both directions, right? It can accommodate your output voltage. Otherwise, if VC is too close to VCC, right? So you see that your output signal will get cut off. It will not, because the maximum voltage is VCC, it can't go beyond that, right? You can get negative half, right, properly, but you will not be able to get positive half. it will get cut off. Or if VC is too low, right, very close to VB, still it is reverse biased, you will say that it is in active mode, but it is in active mode, but it will not be able to, accommodate the negative half of the signal. You get cut off here, right? So you will not get the correct, signal at the output. It will get distorted, get chopped off, right? So because your biasing circuit is not properly designed, right? It is not designed to sustain the output voltage and current that is needed by your load. So it is not just forward biased and reverse biased, right? It has to be, appropriately designed so that collector current is large enough so that it can support your load current, right? The maximum value of the load current. And also it can support the maximum value of the output voltage that is needed by the load, right? So these two things are crucial. And so designing the biasing circuit, the two parameters, VC and IC, right, are very critical, right? They have to be properly, set, right? You have to first find out what is the value, right? What should be the value of VC? What value of VC you should set, right? So that your amplifier is able to support your output voltage, and what should be the value for IC so that it can support the load current, right? So that first you have to determine. Once you have determined that, then you go for designing the amplifier, right? So then what should be the values of RE, RC, right, to satisfy this requirement, right? So that you get these correct values for VC and IC. As you know that IC and VC, IC is almost equal to, IC is given by alpha IE. So that you know that IE is alpha is almost equal to 1. So we can write IC is almost equal to IE. Right? So these two currents basically almost same. So if you can fix IE, you can fix IC. So that is how you fix IC. You first determine how much is demand of the load current. From that, you determine how much should be the collector current. And then IC is almost equal to IE. So then IE value should be that. And in order to determine the value of IE, you use this equation, right? Okay. From this equation, we can write that IE should be, if we rearrange the terms, VB, that minus VBE, right? And that divided by RE, right? So from that, from this expression, you can fix the value. You vary RE, you vary IE, right? Very simple. So first you need to also fix the VB for that. And VB also we have shown this as the voltage division rule here. We apply, right? You get VB. VB is, you have R1 plus R2 and VC, right? So by adjusting the values of R1 and R2, you fix the value of VB. And by adjusting RE, you fix the value of IE, right? So this is how we design, right? You fix the value for IC, right? And so once IC is fixed, right, you know the value of how much VC is needed, then you use this equation here, right? This equation here. And try to find out what should be the value for RC, right? So that you get this value for VC, collector voltage, right? And of course, this voltage has to be greater than VB, right? To ensure that this is, so VCB also has to be this voltage, right? So this is how you design the biasing circuit of the amplifier, right? That will need, right, that will meet the voltage and current requirement of your load, right? So VC, by designing the biasing circuit, the VC and IC, these two parameters are very important. And these two parameters together are also known as the quiescent point. I don't remember the actual spelling of this, QISI, whatever. Called the quiescent point. Have you heard of this one?
No, sir.
No, sir.
You're supposed to know this because I think this is there in device 1, the quiescent point or operating point. These are known as the quiescent or the operating point of the amplifier, because the load voltage and current will vary right around this value, right? The output voltage VC, right, varies around VC, the collector voltage, DC voltage. The output current IC, the load current will also vary around this collector current IC. So these two parameters together are called the quiescent point or the operating point of the amplifier, and these are the very important two parameters when you want to designing the amplifier, not just the gain. Right? There are other issues. Gain is one of the factors. There are voltage and current. How much voltage and current is needed by your load, and accordingly you have to design. And you start designing the amplifier, starting with designing the biasing circuit, right? So design the biasing circuit so that it can have that appropriate value of VC and IC. So that's the first step in designing the amplifier. Any question, guys?
No, sir.
No, sir. No, sir.
Okay, so today's time is up, so we'll stop here. So we have discussed the conceptual circuit diagram of different amplifier configurations, and we have discussed the different issues that are involved, right, in designing the biasing circuit for the amplifier. Okay, guys, I shared this one.